Pencast number 8. This is problem 7.44 from Griffiths. We have a conductor, so the E is equal, that's a weird looking E, whatever, equal to 0 inside. And all the charge resides on the surface. So on part A, we're supposed to show that the magnetic field is constant inside. We have E dot dl equals the negative integral of the partial of B with respect to t dotted with dA. E equals 0, so we just have the integral of 0 dl here, which is 0, equals negative partial of B with respect to t dotted with dA, or partial of B dt dA. Since this right here doesn't have a area determinacy, it's all dependent on time, then we get negative partial B respect to t times the area. The area is not 0, the cross-sectional area, thus that means the partial with respect to t has to equal 0. Part B. Show that magnetic flux through the perfectly conducting loop is constant. So, magnetic flux is equal to the integral of B dotted with dA. Then if we take the negative partial of this flux with respect to t, we get negative partial with respect to t.
Sorry.
Fine. Oh.
It's just going to be like...
partial of the flux with respect to t gives a negative partial with respect to t of B dot dA. Since this is a spatial integral right here, we can put the partial with respect to t in. Since we found up here the partial of B with respect to t is equal to 0, this part just goes to 0, and the integral of 0 dot dA equals 0. Thus, the magnetic flux is not changing through the loop, and we can say the magnetic flux is equal to a constant. Alright, part C. Part C, we need to show that the current in the superconductor is only confined to the surface. So we start with the full thing of Ampere's law. I think this is Ampere's law. I'm not really good with these names. Anyway, this thing right here. Whichever law this is. Alright. So B is a constant, and since the curl of B depends on the derivative of B, that just goes to 0. Similarly, we have E is equal to 0, so the change of E with respect to t equals 0. So that term goes to 0. And then we're just left with mu naught J equals 0. Mu naught does not equal 0, that's a constant. Thus, we have J equals 0, which means there's no current inside of the sphere, which means it only lies on the surface, which proves that which just proves the charge is all on the surface. And current's all on the surface. Okay, last part, part D. Now we have this sphere that has a magnetic field in the z direction, and it is brought to a temperature greater than the critical temperature, and we're dropping it to there and finding what the surface density K is at as a function of the polar angle, which we'll define as the angle we'll define as theta.
Hey, Huey, leave it. Oh, never mind.
Okay, so this magnetic field can be found from equation 5.70, where they solve for this type of sphere as 2/3 mu naught sigma omega r in the z hat direction. And we have omega equals omega in the z hat direction. We can start by relating V with omega, so v is equal to omega cross r, which equals omega in the z hat direction, cross with the r vector, which gives omega, and we're going to call, it's a, not big R, omega, so we have omega a sine theta, or omega equals v over a sine theta. Then we can plug that in, and we have b naught in the z hat direction is equal to this term right here, 2/3 mu naught sigma v over a sine theta times a. This r right here is also a. And then we can do some canceling with the a, and we now have k is also defined as sigma times v, or sigma v in the theta hat direction, since v is moving around. Then we get b naught is equal to 2/3 mu naught k times 1 over sine theta, and putting it all together and moving k to the other side equals 3 b naught sine theta over 2 mu naught in the theta hat direction. Done.
Oh, good.